Hello everyone, once again I am Roseto Orquesta and welcome to Pantasmalaya. Okay, so this is a continuation of the previous video about the different times and the process management. And in the previous video we talked about the scheduling algorithm, and we talked about the first come first serve and then the round robin. And in this session, in this video, we'll talk about the rest of the scheduling algorithms that is present in the process management. So among the scheduling algorithms is the shortest job first. So this algorithm, this scheduling algorithms will look into the burst time of each of the processes. So instead of um, if the first come first serve will look into the arrival time of each of the processes, and then the round robin will provide a quantum slice for each of the processes to be executed until all the processes are executed in the central processing unit. The shortest job first will look into the burst time of each of the process. Yeah. The shorter the burst time, um, it will get the time of the central processing unit. So, say for example, if we look at in this example, this table, so we have at least 5 processes, and this processes has different burst time. We have 6, 2, 8, 3, and 4. Now, among this burst time of each of the processes, since this is shortest job first, it is very noticeable that process 2 will get executed first from the rest of the processes. So it should be process 2, and then process 3, process 2, process 4, process 5, and then we have process 1 and process 3 as last, since process 3 has the longer burst time of 8. If that's the case, but we still have to look at the arrival time of each of the processes. So in this case, it has different arrival time. So the first one to arrive at the processing for the central processing unit is this P4, and it has three burst time. So this will get the CPU first, the time of the central processing unit first, because this is the first process that gets the or arrive at the starting line of the queues. Now, to look further and understand better the algorithm of shortest job first, we'll move to the next slide. So you have here a Gantt chart of the previous table. So in the table, as you can see here below, so the first process that arrived is P4, since its arrival time is 0. So it gets the CPU first. It arrives at 0, it get executed at starting time 0. And then process 4 has a burst time of 3. So it will be finished at time 2, 0, 1, 2. So at around time 2, process 4 is already finished. But at around time 1, process 3 has arrived. As we if we look at into the table below, process 3 has an arrival time of 1, so therefore it should be implemented in the Gantt chart that process 3 arrived unqueued at time 1, while the process 4x is in execution process. And then on time 2, P1 has arrived. Since here in the table below, P1 has arrival time of 2, just after the arrival of P3. So therefore, P1 is being added into the queue, just like after the P3. So P3 is already in the queue, and then P1 is added into the queue as it arrives at time 2, while the process 4 is still in execution process in the central processing unit, because P4 is the first process that arrives. Okay, and then on time 3, now we have here on time 3, no process has arrived at time 3. As you can see here, we have 0, 1, 2, and then 4. So there is no process that arrives at time 3. So this is why we left the green block here as empty. But during the time tree, since P4 has already been executed, has already been terminated at around time 2, so we have to decide, or the central processing unit has to decide which one of the queues, the queue processes will be executed first. And in this case, since this is a shortest job first, we have to compare the burst time of P3, process 3, and the burst time of process 1. Now, since the process 3 has a burst time of 8, and then the process 1 has a burst time of 6, it is true that P1 has a lesser burst time compared to P3. So in that case, P1 will begin in its execution at time 3. So it will get the attention of the central processing unit at time 3, this process 1, since it has only a burst time of 6 compared to P3, which has a burst time of 8. We do that because this is a shortest job first. Then on time 4, process 1 is still in execution, while there is another process that arrives at around time 4, and that is the process 5, as you can see here in the table below. So process 5 with burst time 4 has arrived at time 4. So this is why we add P5 in the green block, and then added to queue next to the process 3, which is in queues, the process 3, while process 1 is still in execution. And then on time 5, another process has arrived in the queue, and we have the process 2. As you can see here, it arrived at around time 5, so we put P2 here at time 5 and then added it to queue next to P5 and P3, while P1 is still in execution. And then at around time 6, so P1 is still in execution because P1 has a 6 burst time. So we count from time 3, time 4, time 5, time 6, time 7, and times 8. So if we count that way, we have 1, 2, 3, 4, 5, 6, 6 execution time, 6 burst time for P1. Now in P9, since P1 has already been committed, has already been executed, or has already finished in execution at time 8, at around time 9, we have to compare. So at around time 9, we have to compare uh, the burst time of P5 versus P3 and P2. Since these three are already in queue and no new process arrived at time 9. So what we did is we left the green block as blank, and then we need to compare the burst time of process 5, process 3, and process 2. And in this case, process 5 has burst time of 4, and then process 3 has a burst time of 8, while process 2 has a burst time of 2. That means process 2 will get the time of the central processing unit. So this is why P2 is executed, starts its execution at time 9, because P2 has only 2 burst time compared to P3 that has 8 and P5 that has 4. So P2 will be an execution and will be processed by the central processing unit from time 9 up to time 10. So it will accommodate to occupy two blocks of time or two slices of time in the central processing unit, since it has a burst time of 2, while the uh, process 5 and 3 is still in queues. And then since process 2 has finished its execution or has been committed at time 10, therefore at time 11, we are going to compare the two remaining processes, which is the P3 and P5. Now we have to look into their burst time. And since P3 has a burst time of 8, while P5 has a burst time of 4, that means P5 will get the execution time, will get the CPU's time. So it will be processed in the central processing unit, this process 5, because it has only 4 burst time compared to P3 that has 8 burst time. Now from time 11 to 12, 13, 14, 15, 16, 17, 18, and 9, no, from time, so from time 11, 12, 13, 14, the central processing unit will process the process 5 and put process 3 in queue. So in total, if we count from 11 up to 14, we have 1, 2, 3, 4 burst time, 4 slice time. That is equivalent to the burst time of P5. Now, since there's only one process that left in the queue, and that is P3, which has 8 burst time, it will be then executed or start its execution at time 15. So from 15, 16, 17, 18, 19, 20, 21 up to the 22nd slice of time, process 3 is being accommodated by the central processing unit. Now, if we count from time 15 to time 22, we have 1, 2, 3, 4, 5, 6, 7, 8, 8 slice of time that is equivalent to the burst time of process 3. Now, that is how the shortest job first works. So, first, the first job will get executed, the one that arrived first at the queue, and then when another process comes in, it will wait the first job to be completed, and then if there's another uh, process that goes in for the queues, these two processes that are present in the queue will be compared, which of this process has a shortest burst time, so that those process that has the shortest burst time will get the CPU first. And that is how the shortest job first work. Now, same from the previous algorithm, the first come first serve, the round robin. Uh, this the wait time has the same formula, which is the execution time minus arrival time. When you say execution time is it talks about the total length of slice of time it gets to execute. Now let's look at this. P1 has execution time of 3. Why does the P1 has the execution time of 3? Because in this Gantt chart we have time 0, 1, 2, and on time 3 P1 was first executed at time 3. So we have recorded here that on the third time, the process 1 has started its um, processing or execution in the central processing unit. Then since it has an arrival time of 2, so we have to subtract this time 3 minus 2, so that is why we have 1. Now on the process 4, and now process 2, it has an execution time of 9. So it says that it's an execution time of 9. As you can see here in our Gantt chart, process 2 is getting the central processing unit at time 9. So that is why we have here the 9. And then this 5 is the arrival time. So 9 minus 5, we have now 4 waiting time. And then for the process 3, that is 15. So if we look at into the time 15, we will see that P3 first got the central processing unit for execution at time 15. So that is why we have here time 15 minus 1, because its arrival time is 1, so we have 14 waiting time. While on the process 4, since it is the first to arrive at the queue and then gets executed at that moment, so it has a 0 on the time slice of execution, and then it also has a 0 for the arrival time. So there is nothing change in the wait time. So it waits not less than 0 time to get executed in the central processing unit. Now in process 5, it has an 11, because if we try to look at into our Gantt chart at the process at the time slice of 11, P5 is getting the attention of the central processing unit at time 11. So that is why we have here 11 minus 4, and this 4 comes from the arrival time of the process 5. So we have 11 minus 4, that it means process 5 has wait 7 uh, time slice to get executed. So for the average waiting time, we are going to sum up this wait time, which is 1, 4, 14, 0, and 7. So 1, 4, 14, 0, and 7, and then divided by 5. This 5 comes from the total number of processes, which is 1, 2, 3, 4, 5. So the answer is of the average waiting time is 5.2. So that is how the shortest job first works in the as an scheduling algorithm in the central processing unit. Now, another type of a shortest job first is a preemptive Sfg scheduling, or a preemptive shortest job first scheduling. We have here an example table for the preemptive SGF scheduling. So we have the burst time and then the arrival time. So I guess this is just the same processes: 6283, 62834, and then 2510. So 2510, 0 have 4. So still, this process should be the example and the shortest job first, but the preemptive is GF scheduling. Now, what happens in the preemptive scheduling algorithm of shortest job first, that if you look at in this Gantt chart, you will notice that there are blocks of colored blue added into the Gantt chart, instead of the previous one that has only this green, yellow, and red aside from the time. Now we have blue. So in this manner, so since the process 4 is the first that gets the execution time, because it has an arrival time of 0, so it will be executed from time 0 to time 2. And then from around time 1 and time 2, we have two processes arrive at the queues. We have P3 and P1. And then at the time 3, just like the previous Gantt chart, we will compare the burst time of P3 versus the burst time of P1. So in this case, P1 will win the central processing unit because P1 has 6 burst time compared to P3 that has 8 burst time. Now P1 will start its execution at time 3, but then at around time 4, another process has arrived, which is the P5, process 5. It will be added in the queue, and then since there is a new process that arrive, the the execution of process 1 will be halted and will be compared to the queues. So P5 now will be compared to P3, P1, and P3 and P1's burst time. So in here, it will notice that the P5 P5 has 4 burst time compared to P1 that has 5 burst time. Why 5 not 6? Because it's already the P1 has begun its time, or the execution at time 3, so it's already been deducted one time, so it is now P1 has now 5 burst time during the time 4, but that burst time, which is 5 for process 1, is still longer than the burst time of process 5, which is 4. So in this case, process 1, that is the current process in the execution, will get preemptive, or it will be paused, it will be halted. And then P5, since P5 has the shortest burst time compared to 5 and 8, so P5 will now get the attention of the central processing unit. It will be executed in the central processing unit while P1 is being paused or halted, while P3 remains on the queue since P3 has a burst time of 8. And then on time 5, another process has arrived in the queues, and that is the process 2. Now since it happened, process 2 will be then compared, the burst time of process 2 will be then uh, compared to the burst time of process 5, process 3, and process 1. Now, in this case, process 1 has 5 burst time because it is already deducted 1 from time 3, and then the process 5 has 3, so 5 and 3, and then uh, P3 has still um, 8 burst time, while 2 has a process 2 has only 2 burst time. So since process 2 has only 2 burst time compared to P1 that has 5 and P5 that has 3, P2 has the shortest burst time. So process 2 will get the attention of the central processing unit, while P5 will be added to or preemptive, just like the previous P1. So there are two preemptive processes now. We have P1 and P5. And then since they are preemptive, they are priority but still be added into the queue with P3. So we will now have P3, P1, plus P5 as the new queues for execution. But the real status of this P1 and P5 is preemptive. Preemptive since they are already executed, but it happened that a new process with the shortest burst time arrives at the queues. So the current P1 and P5 gets preemptive instead. Now, since P2 has 2 burst time, it will be executed from time 5 and time 6, as you can see, while the queues is P3, P1, and P5 with status P1, P5 as preemptive. Now, since P2 has only burst time of 2 and is already executed completed at time 6, at around time 7, the central processing unit will compare the burst time of P3, P1, and P5. Now, in this time, the time 7, P3 has still 8 burst time, while P1 has now 5 burst time, since it is already deducted 1 on the first time it it gets the CPU, and then P5 has 3 burst time. Now, to compare 3 versus 5 versus 8, P5 has the lowest or the shortest burst time, which is now 3. So that's why P5 will get the central processing unit's attention at time 7. So P5 will get its moment and being executed in the central processing unit from time 7 to time 8, time 9. So it has additional 3 execution time, while P3 and P1 is still in the queue. Now, since P5 has finished its execution at around time 9, on the next time slice of time 10, since we have queued P3 and P1, we will compare now, or the central processing unit now compare the burst time of P3 and P1. Since P3 has still 8 and P1 has 5 burst time, uh, P1 will win the competition to get the attention of the central processing unit. So in this time 10 slice, P1 will be executed by the central processing unit, while P3 will put back into the queue. So from time slice of 10, process 1 will be in execution or will be processed by the central processing unit until time slice 14. Now, if we count that, we have time 10, 1, 2, 3, 4, 5. So we have now 5 since P1 has 5 remaining time slice for execution. And since at around time 14, P1 has finished its execution at time 15, to time 22, P3 will get the central processing unit for itself and P3 will be processed 8 time slice, which is the burst time for process 3. So we have 15, 16, 17, 18, 19, 20, 21, 22 burst time of that is equivalent to 8 burst time from 15 to time 22. Now, as you can see in the table below, the wait time, it says execution time. The formula is execution time minus arrival time. But on on process 1, we have here 3 plus 2 plus 6. So this means that at around time 3, this 03, the process 1 gets the attention of the central processing unit. As you can see here in the Gantt chart, you can see that P1 first gets the central processing unit at time 3. So we have 3. And the arrival time is 2. So we have here 2. So 3 minus 2. But then we have the plus 6. Where do we get this plus 6? It is because when the P process 1 is start its execution at time 3, but it is preemptive or halted at around time 4. Now, process 1 regain its execution time at around time 10. Now, if we count that from time 4, we have um, we have 1, 2, 3, 4, 5 waiting time. So there is another uh, waiting time of 5. So it is here that on the process 6, we have here a 0 plus 6 um, to the answer of execution time plus arrival time because of this preemptive status from time 4, and then regain the control of the central processing unit at around time 10. So if we count on it, we have uh, 1, 2, 3, 4, 5. 5 waiting time, and then another waiting time from P2. So it arrives at time 2, and then we have the first execution time of P1 is in time 3. So we have here the 3 here. This is the original execution time of process 1, and then deducted by 2 or subtracted by 2 because of the arrival time. But since it is preemptive at around time 4 and gets the central processing unit at around time 10, we have to count more waiting time. So this is another waiting time, this plus 6. So how do we get to plus 6? We have to count the time 5 up to time 9. So 1, 2, 3, 4, 5. No, from time 4 to time 9. So we have 1, 2, 3, 4, 5, 6. So from time 4 to time 9, it is equivalent to 6. So 3 minus 2, we get 1, and then plus 6, it has now a total waiting time of 7. So for process 2, 3, and 4, there is no waiting time since when it arrives at the queue, like the process 2, it has the shortest burst time, so it gets the central processing unit um, at the time it gets it arrives at the central at the queues. So just like the P3, there is no additional waiting time because it process 3 has not experienced a preemptive since it arrives at 15. Here it arrives at 15. It execute at around 15. It finished its execution at 22 without being preemptive. So that is why 15 minus 1. So 1 comes from the arrival time of 1. So it only waits 14 time slice to get executed. While the process 4, since it is the first to arrive at the queues, it has a 0 arrival time. So it didn't wait for any other process. When it first arrived at the queues, it gets the attention of the central processing unit as well. So it is being executed at that moment. So we have a 0 waiting time for process 4. While the process 5, uh, it it arrives at the time 4. So here we have a time 4 since process 5 arrives at time 4, and then we have the arrival time of 4. So we are going to subtract, which is uh, 4 time 4 for the process 5, the time of arrival execution. So it arrives and it executes at time 4. So and since the arrival's time is also 4, so we have 0, and then we have 2 here because process 5 is being halted or preemptive at the time slice of 5 up to time slice of 6 before it regains the attention of the central processing unit, because at time 5 process 2 has arrived in the queues, and process 2, as you can see here, has the lowest burst time. So at time 5 process 2 gets to executed at the central processing unit. So process 5 is being preemptive with process 1. So this is why we have additional 2 waiting time here. That 2 will comes from time 5 and time 6, because uh, process 5 halted at time 5, or preemptive at time 5, and then queued at time 6 and regain its time to the central processing unit at time 7. So we have 5, 6, that is equivalent to 2 additional waiting time. So we have 4 minus 4 equals 0 plus 2. That is why we have 2 waiting time for process 5. Now to get the average of the waiting time of all the processes, we have to sum up again the waiting time of each of the process. It is 7 plus 0 plus 14 plus 0 plus 2, and then we will divide it into 5 since we have 5 processes, and then we get the 4.6 average waiting time for this. So the main difference between the shortest job first which is not preemptive, is that um, it will wait for the current it will wait for the current I'm sorry, it will wait for the current um, process that is in execution to finish, and then um, compare the burst time of the current processes which is in a ready queue. But on the preemptive, it will not wait for the process that is currently being executed in the central processing unit, but it will halt that process, then to make a new comparison between the process that is in queue and the new arrival process, the new process that arrives in the queue. So every time that there is a new process arrives, it will pause, it will halt the processing in the central processing unit to make a new comparison for each of the processes for the burst time, and then to get to decide which of the processes will be given a priority to be executed in the central processing unit. So that is the main difference between the preemptive and the non-preemptive. In the non-preemptive, if there's new process that arrives in the queue, it will wait for the current process to be finished, then compare the first time of those processes in a ready queue. In preemptive, it will not wait for the current process to be finished, but it will halt the current process, and then create a new comparison, a new compare the process of uh, the new process that arrived to the ones that are already in the queues, and to the process that is already uh, processed or in the central processing unit. And then if it happens that the process in the central processing unit, or the one that is currently in processing mode, has a longer still has a longer burst time compared to the newly arrived process, then that current process in the central processing unit will get uh, will be halted, or will be paused, will be preemptive, and then it will be replaced by the new process that arrives at that at that slice of specific slice of time. So that is the main difference of um, shortest job first and preemptive shortest job first. Now the next scheduling algorithm is the shortest remaining time first. So in here, it is the preemptive form of SGF. And in this algorithm, the OS schedules the job according to the remaining time of the execution. Now we add the concepts of varying arrival times and preemption of the analysis. Now we have here four example processes in a queue. We have P1, P2, P3, and P4. And then it arrives at a different time. So we have 0, 1, 2, 3. And then the burst time differs also. We have 8, 4, 9, and 5. Now for the shortest remaining time first, since P1 has arrived at time 0, it will be executed at time 0. At at around time 1, as you can see here, process 2 has arrived in the queue. Now, in this one, since a new process arrived in the queue, in the ready queue, it will be compared. So it will compare the it will compare the remaining burst time of process 2 versus process 1. Now, since process 1 has already executed at around time 0, so the burst time of process 1 is already has is already subtracted by 1. So, according to the table, P1 has burst time of 8. So, at around time 1, P1 now has a burst time of 7. So, 7 versus the burst time of 2, and then the burst time of process 2 is only 4. So process 2 will get the time of execution in the central processing unit because it has a shortest burst time, remaining burst time compared to the remaining burst time of the process 1, which is 7. Now at around time 2, So a new process has arrived in the queue, which is the process 3. And since there is a new process arrived at the ready queue, the system or the central processing unit will compare the remaining burst time of process 2, process 1, and process 3. And in this, because process 2 has been at executed at around time 1, so we have to deduct 1 time slice of the process 2. So process 2 that has a burst time of 4 now becomes 3, while the burst time of P1 is still in 7, so 7 and 3. Now since we have 7 and 3 compared to the burst time of process 3 has 9, so still, process 2 will get its execution in the central processing unit since it has the shortest remaining burst time compared to process 1 and process 3, which has process 1 has 7 and process 3 has 9. So at around time 3, another new process arrived at the ready queue, that is a process 4. Now since there is a new process arrived in the queue, we are now the system now will compare the remaining burst time of process 2, process 1, process 3, and process 4. And if we go back to the previous slides, since the burst time of P1 is already 7, and then the burst time of 2, um, since we executed a burst time of 2 here of from time 1, time 2, and then time 3, no, on time 1 and time 2, so it has now an execution time of a burst time of that's now burst time of 1. So at around time 3, the current burst time of P2 is 1. So since the current remaining burst time of P2 is 1, it will still get the attention of the central processing unit because 1 compared to 7 and compared to 7 and compared to 9, so 2 will finish its execution at the next time slice. So we have here from time 1, time 2, time 3, and time 4. While the process 1, 3, and 4 is in the waiting in the ready queue. Now since P2 has burst time of 8, so it is executed from time 1, 2, 3, and 4. Process 2 finish its execution at time 4. So at around time 5, the system will now compare the remaining burst time of P1, P3, and P4 that is in the uh, waiting queue or ready queue. Now since P1, according to the table, uh, process 1 has already executed once, and then um, this P3 has not yet being executed at least once, while P4 2 has not executed first. Now we are going to compare the system now will compare the values of 7, 9, and 5. So because P4 has a burst time of 5 and that is less than to the burst time of P3, which is 9, and less than to the burst time of P1, which is 7. So P4 will get the attention of the central processing unit, and it will be executed from around time 5 up to time 9. Now, if we count from time 5 to time 9, we have 1, 2, 3, 4, 5 uh, time slice, which is equivalent to the total burst time of P4. Now at around time 10, so at around time 10, the system will again So here at around time 10, the system will so at around time 10, so here, so then at around time 9, process 4 has finished its execution. So at around time 10, the system will compare the remaining burst time of process 1 and 3. Now in this case, if we look back in the table, since P1 process 1 has already executed once in the central processing unit but gets halted because of the new process. Now the process 1 has 7 burst time, remaining burst time, while compared to process 3 that is still 9. So 7 compared to 9, process 1 will get the time of the central processing unit. So from time 10 up to time 16, as you can see here in the Gantt chart, from time 10 to time 16, process 1 is being executed in the central processing unit. And if we count this, from time 10 we will get 1, 2, 3, 4, 5, 6, 7, then plus the first time it is executed in the central processing unit in a time 0. So that totals to 8 execution time, or 8 slice of time, or 8 burst time. So again, we are going to count the execution of process 1 from 10 up to 16. That is 1, 2, 3, 4, 5, 6, 7. And then plus the time 0, which is the first execution time of the P1 before it is halted by the process 2. So we have 8. And then since there is no more uh, process in the ready queue, and aside from process 3, at around time 17, process 3 will get the attention of the central processing unit, and it will be executed from time 17 up to time 25 slice. And if we count here from 17 up to 25, we will get 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have a 9 times slice, or 9 burst time, which is equivalent to the burst time of the process 3 in the table and in this slide. So the difference between the shortest remaining time first and the shortest job first is that and the shortest job first, it will compare the burst time, the total burst time of the processes, while in the shortest remaining time first, it will compare the remaining burst time. So it will not look into the how is the total burst time of a process, but the actual uh, burst time of the remaining burst time of the process. So if it gets executed first, then halted, then instead of comparing the total burst time again, it will only compare the remaining time, or the remaining burst time of that process that is halted by the system with another or new process that arrives in the ready queue. So that is the main difference between shortest remaining time first and the shortest job first. So in here we have the wait time. For the wait time of the shortest remaining time first, so we will have to look at the execution time and the arrival time. Okay, so if you can see here at the process 1, we have 0 minus 0 plus 10. This happens because process 1 arrived first in the central processing unit and gets executed at time 0. So that is why we have here a 0 execution time minus 0 for the arrival time. But this plus 10 happens because at around time 1, process 1 is being halted by the system because it gives way to the process 2. Now the process 1 regains its time in the central processing unit at time 10, as you can see here. So process 1 regains the central processing unit for execution at around time 10. So we have to count that the gap from time 0, which is the first execution time of the process 1, up to the time 10. So we will count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is why in this table we have to add 10 time slice to the waiting time, because process 1 has to wait 10 time slice before it gets back the attention of the central processing unit. So that is why 0 minus 0, we have 0 plus 10, so it has a total 10 time slice for the waiting before it gets executed in the central processing unit. And then we have the process 2, which is we have 1 because according to our Gantt chart, process 2 arrive at time 1. Oh, this is the arrival time. No, this is the execution time. So it arrives at time 1, it gets executed at time 1. So that is why we have 1 here for the execution time, and this another 1 here from the arrival time. So execution time of process 2, which is 1 minus 1 of the of its arrival time, we have 0. And then for the process 3, it has an execution time of 17. So if we look back into our Gantt chart, at around um, time 17, process 3 has its time with the central processing unit to be processed from 17 to 25. So process 3 starts its execution in the central processing unit on the CPU at around 17. So that is why we have here 17 minus 2. 2 comes from the arrival time, so we get 15 waiting time. And same happens with the process 4. Process 4 gets its execution time at time 5, time slice 5, and the slice here, as you can see here. So process 4 execute first execution is around time 5. So that is why we have here 5 execution time and minus 3, since the arrival time of process 4 is 3. So we get 2 waiting time for the process 4. Now to get the average waiting time, we have to sum 10 plus 0 plus 15 plus 2 and then divided by 4. This 4 comes from the total number of processes we have in this example. We have P1, P2, P3, 4, that is equivalent to 4 processes. That is why we divided the sum of 10, 0, 15, and 2 into 4. So we get 6.75 average waiting time for this example of the shortest remaining time first. Now the next algorithm is the priority based scheduling. So in this algorithm, the priority will be assigned to each of the processes. The higher priority, the sooner will the process get the CPU. If the priority of the two processes is the same, then they will be scheduled according to their arrival time. So in here, as you can see, in the example, we have first time and priority. So according to the table, the first priority to be executed in the central processing unit is P2. So in our Gantt chart, it should at time 0, we will have P2 for its execution at time 0. And then at around time 1, so at around the next one, at around time 1 to time 5, we have P5. So if we look here at the process 5, it gets a second priority. So P5 get the second priority. So after the P2 is finish its execution in the central processing unit, P5 gets the time for its execution in the central processing unit from time 1 to time 5, since it has a burst time of 5. And then after the P5 finish its execution, the next in priority list is the P1. And the priority, we have priority number 3, P1. So P1 has burst time of 10, so it will be executed from time slice 6 to time slice 15. So after the time slice 15, P1 is finished its execution. The next in the priority list is P3, which has a burst time of 2. So if we look into our Gantt chart, you can see that at time 16 and time 17, P3 has its execution time in the central processing unit for 2 burst time, since it has a 2 burst time, the P3. And then for the last in the priority list, we have the P4, and that P4 has a burst time of 1, so that is why at time 15, or only at time 18, I mean, P4 is get its time to be executed and got its time in to be executed in the central processing unit. So to compute the waiting time, we have to look into its execution time minus arrival time. So here in the table, for the process 1, we have 6. We have 6 for the arrival time. I know execution time. If we look into our Gantt chart, at around time 6, the P1 gets its first execution time in the central processing unit in the CPU. So we have 6. But then we have arrival time at 0, because as you can see here in the table, in the example table, so since there is no given time of arrival, it is safe to assume that all processes has arrived at exactly um, 0 time. So since there is this kind of information, you have to be careful, because if you see that there is no arrival time included in the table, you have to um, you have to assume that all of the processes arrives at um, 0 time simultaneously. Okay, so since it is 0, as you can see here, to waiting time, the arrival time, we have here 0 for all other processes. Because in our table example, there is no a specific column for the arrival time of the processes. So we assume that they all arrive at 0 time, respectively, simultaneously. And then we look for their execution time with our Gantt chart. So process 1 at around time 6, process 2 at time 0, process 3 at 16, time 16, and then process 4 at time 18, and then process 5 at time 1. So 6 minus 0, 6, 0 minus 0, 16 minus 0 equals 16, 18 minus 0 equals 18, 1 minus 0 equals 1, and we have to sum this total wait time to be divided by the total number of the process. So we have 6 plus 0 plus 16 plus 18 plus 1 divided by 5. We have 8.2 as the average waiting time. So that is how the priority-based scheduling works. So in this video, we talk about the shortest job first, the preemptive shortest job first scheduling. We also have the shortest remaining time first, and then the priority-based scheduling. And then in the next video, we will talk about the highest response ratio next scheduling algorithm. So if you have questions and clarifications regarding on this scheduling algorithm, so please comment down below, so that we will try to answer your inquiries in the next video. Thank you.